Not only is the Earth not the center of the universe, but there must be other worlds out there. There must be other inhabited worlds out there. Of course, Bruno was burned at the stake for his heretical thoughts. And it would take us another 400 years before we would get any data. But in this is very frustrating. But in 1992, the first extrasolar planets were detected. They happened to be orbiting a pulsar, which is the dead remnant of a star after it's gone supernova, not very inhabitable. And in 1995, the first exoplanets were discovered around a sun-like star. So this is a planet around the star 51 Pegasi by Michael Meyer and Didier Queloz, a couple of European astronomers. The interesting thing about this planet is that it's about half the mass of Jupiter, but it orbits its star in only 4 days, much closer to the star than Mercury. It's what has been termed by astronomers as to be a hot Jupiter, which is a class of planets which we do not have in our solar system, as you all know. Up till 1995, when we're looking out at the universe and we're thinking about the planets around other stars, we assume that our solar system must be typical, because we have great theories for why the small rocky planets should be close to the star and why the big cold gas giants should be far around from the star. Our theories about formation of the solar system naturally lead to that. And so the discovery of a hot Jupiter, which is totally impossible according to our theories of planetary formation prior to this discovery, really threw the planetary formation theorists into a tizzy. A lot of work has been done since then. There are 5 major methods for discovering planets around other stars. The radial velocity method, where you look at the star, you look at the spectral lines in it, and observe Doppler shifts as the star wobbles to and fro as a planet goes around it. That's the way 51 Peg B was discovered, the first one. Now, if you think about it, the bigger the planet, the bigger the wobble, right? And the closer the planet to the star, the faster the wobble. If you want to watch our sun from far away to see Jupiter, you have to wait 12 years to see a wobble. But of course, on 51 Peg B, you only had to wait 4 days to see a wobble. So the easiest planets to find with the radial velocity method are big planets close to the star, and that's why the hot Jupiters were the first ones discovered through this method. Astrometry is the oldest method. When I was a student, I know there were people who were looking at Barnard's star and trying to see if, as it moves through the sky, it wiggles back and forth in the plane of the sky from the same thing, this planet going around the star. So that's another way to see it. Transits are the ones that we have found most of the exoplanets by, and I'll show you a picture of it. But briefly, as a planet goes in front of the star, it blocks out a little bit of the starlight, and you can observe that dimming in the starlight, and from that, detect the presence of the planet. Microlensing, I'm not going to talk about that, but if one star gets in front of the other star, Einstein's theory of general relativity says that as the back star's light goes past the front star, it gets lensed by the gravity, makes it a little brighter. If there's a planet next to the nearby, the closer star, then the planet can also do some lensing, and you can detect the planet by its gravitational impact on the background star's light. And finally, direct imaging. If we could actually take pictures of stars and planets next to each other and be able to pull out the planet from the glare of the star, we could detect it that way. So I've already told you about the radial velocity method, which is the most common method used from the ground, where we have big telescopes with very sensitive spectrometers to detect the wiggles in the star. On August 24th, just a month ago, astronomers in Europe announced the discovery of a planet around the nearest star to the sun, Proxima Centauri. So we know, I didn't touch it. So we know that there are exoplanets around the nearest stars, and these are wonderful targets for us to study. I did not do that. Proxima Centauri, of course, is a very small star. It's only about 1/10 the mass of the sun. It's only about 0.2%, 1/500th the brightness of the sun. The planet that was discovered goes around the star in 11 days, so it's very close to the star, but because the star is so faint, Proxima Centauri is actually in the habitable zone of Proxima, and I'll talk a little bit more about habitable zones in a moment. And the planet is, I did not do that. The planet is 1.3 times the mass of the Earth, and as I'll show a little bit later, we think a planet that's that small is likely to be rocky. So this might be this might be a rocky planet in the habitable zone of its star, which is amongst the most interesting planets we're looking for. Direct imaging, this is a picture of Fomalhaut, a bright star in the sky, with the Hubble Space Telescope, where the Hubble Space Telescope has a blocking disk in one of its cameras, so you can block out the light from the star. And that's what the black dot, the black spot in the middle is where the star isn't blocked out. That white dot is just it's just a dot. It's not part of the picture to show you where the star is. But here, where you can't see it, is where the planet is. Pictures were taken in 2004 and 2006. We could see the planet moving. Now this planet is very large, so it reflects enough light that we can see it in the Hubble image, and it's about 3 times the distance of Pluto from its star. I think it's about twice the size of Neptune, so somewhere between Neptune and Jupiter in size, but it's at 120-ish AU away from the star. But that's how far away a planet has to be for you to be able to image it near the star. But as I told you, the method that's been used the most up till now is the transit method. So here's, if Jupiter passes in front of our sun, it blocks about 1% of the light. Yes? Oh, that makes sense. Okay. Right, Jupiter blocks about 1% of the sun's light, but the Earth in front of the sun would only block 1/10,000th of the light. So if we're going to look at distant stars and detect the presence of Earth-sized planets around them, we need cameras that are sensitive to changes in brightness of only 1 part in 10,000, or actually 1 part in 100,000. So we have factor of 10 signal noise. Here's what Venus looks passing in front of our sun. It's easy to see something like that. And then before I jump to Kepler, these are all the exoplanets we found up till now, earlier this year. The dark blue are the ones that were mostly discovered through radial velocity. The light blue and the gold are all the Kepler planets that were discovered through transit observations. So I've mentioned Kepler a couple of times. What is Kepler? Kepler is NASA's first exoplanet mission. It was designed to be able to answer this question: how common are Earth-sized planets in the habitable zone of sun-like stars? How common are Earth-2s in the galaxy? It was launched in 2009, and as I've mentioned, it uses the transit photometry method. Most of the radial velocity planets that I've mentioned before are large ones like Jupiters and Neptunes. We want to look for Earth-sized planets. It's very difficult to detect an Earth-sized planet with the radial velocity method. And habitable zones, so if we're looking near a sun-like star, a planet which is about the distance of the Earth will have liquid water on its surface because it'll be at a temperature of around 300 degrees Kelvin. If you're too close to the star, it's too hot for liquid water. If you're too far from the star, it's too cold for liquid water. The habitable zone is that distance around any star where the temperature of the planet would be right to have liquid water on its surface. If the star is smaller and cooler, the habitable zone is closer to the star. If the star is bigger and brighter, then the habitable zone is further away from the star. And once we know the properties of the star, we can calculate what's the habitable zone of that star. Once we detect where the planet is, we can say yes or no, is it in the habitable zone? The Kepler camera is probably the most stable camera ever made. It's a photometer with almost 100 million pixels on it, had 20 some odd, actually 42 individual CCDs to make up those 100 million pixels. It's stable to actually 1 part in 100,000, so that if we were to observe something which is absolutely the same brightness, then the noise on it would be less than 1 part in 100,000 on that. There is nothing in the universe that we've observed that's actually stable in brightness to that kind of thing. In fact, I'm not going to actually show you any of the squiggle curves from Kepler, but every star we look at varies a lot. And so looking for the dips caused by small planets is a hard problem. And in fact, on Kepler, we require that you see 3 dips evenly spaced, at the orbital period of the planet before we believe those dips are actually a transiting planet. This is the part of the sky that Kepler stared at. It's up in the constellation Cygnus. You can see it's a very large piece of sky. Kepler stared at 150,000 stars for over 4 years, 24/7, taking light curves with 1-minute cadence. Okay, so we've got 4 years of every single one of those stars watching its brightness at 1-minute measurements for over 4 years. Because if you want to look at a 51 Peg-B kind of planet, you only have to look at it for a couple of weeks to see a bunch of transits. But we want to see Earth-sized planets around Sun-like stars. If it's a Sun-like star, the habitable zone is out at 1 AU where the Earth is, and that means the planet's going to take a year to go around. And if we want to see 3 or 4 transits from that planet, we need to stare for 4 years, because the transits are going to be a year apart. And that's the only way we can find these planets. So this is the data from Kepler. Just to show you a scatter plot of what we found. Here is how big the planet is, where these are Jupiter-sized, Neptune-sized, Earth-sized planets. This is the orbital period. Here's a day, 10 days, 100 days. The Earth is here at 300 days and the size of the Earth. And you can see that we see a lot of planets with short periods because they're easier to find. You can see that even though it's easier to find Jupiter-sized planets, that most of the planets that Kepler finds are actually somewhere in size between the Earth and the Neptune. There's another class of planets which aren't in our own solar system. So here's what planets Kepler found. The most common kind of planet are these mini-Neptunes, right? So here's Neptune-sized planets, here's Earth-sized planets. The 2 most common are the super-Earths, which are ones that are 2 to 4 times bigger than the Earth, and the mini-Neptunes, the ones that are half the size of Neptune. Now, it's much easier to see big planets than little planets, right? Because little planets have small transits, which means that you can lose them in the noise. Big planets are really obvious to find. And so this plot has to be corrected for the chance of you missing a planet, okay? Observational bias is what a scientist would call it. So here's the corrected plot. So here's what we infer is the actual frequency of planets of different sizes around other stars based on the Kepler data. So in fact, Earth-sized planets are the most common size. Well, actually, one might hypothesize that Mercury and Mars-sized planets are even more common than Earth, but Kepler isn't sensitive to planets that small. But what we can see from the data is that the Kepler data tells us that the smaller the planet, the more frequent it occurs in planetary systems around other stars. So then the next question is, well, how many of these small planets are rocky, and how many of these small planets are in the habitable zones of their stars? Well, here's that answer for the Kepler data. So here we've plotted the size of the star that we found a planet around. Here's a sun-like star down here, much bigger, a whole lot bigger. And then here you can see how much energy it receives from the star, so the habitable zone moves in as the star gets brighter. And these are all Kepler planets. Ignore the colors. That just had to do with this particular press conference. But you can see we put on it the Earth, the Venus, and Mars. I guess this is, sorry, my bad. This is a sun-sized star. This is a star that's smaller than the sun. This is a little red dwarf star. So we found a lot of planets around red dwarfs, a lot of them in the habitable zone. We haven't quite found the planet, a small planet around a sun-like star. Kepler 452b, you may have heard of that one. That was the one that we called Earth's older and larger cousin. So it's not an Earth twin, it's just an Earth cousin because it's kind of big, might not be rocky, and it's kind of at the edge of the habitable zone. But it's the closest we found so far. But the data analysis is not complete. I expect in the next couple of years there'll be more discoveries. NASA is building and launching next year. Our next exoplanet mission is the Transiting Exoplanet Survey Satellite. It works just like Kepler, but whereas Kepler stared for 4 years at one particular spot in the sky and was looking at relatively dim stars so that it could so there would be lots of sun-like stars in that part of the sky, but they're kind of dim because it was out in the galaxy's arm. What TESS is going to do is it's going to look over the whole sky, and it's going to concentrate on bright and nearby stars. So TESS will find the exoplanets that are transiting around the brightest and nearest stars, which are the ones we want to find so we can follow up with James Webb Space Telescope and large ground-based telescopes, right? The closest stars are the ones where the exoplanets are well, they're easiest to get to, but they're also the ones where the exoplanets look to be the furthest away from the star in the sky. And the bright ones are the ones where there's the most light reflecting off the exoplanet so that we can study it. So TESS is going to give us the finder's catalog of the exoplanets we want to follow up with James Webb Space Telescope, the very large ground-based telescopes, and future telescopes. Now, one final chart here before I talk about the future. What I've plotted here is, with the transit method, you measure the size of the exoplanet. How much light of the star it blocks out depends on the size of the planet. So just by knowing how bright the star is, measuring how much of the star's light is blocked out, then you can calculate what's the size of the planet. With the radial velocity method, which the gravity of the planet causes the star to wobble, you measure the mass of the planet. Okay? If you can measure both for the same exoplanet, you can calculate the density of the planet. Okay? Is it a high density like the Earth, which is made up of rock, or is it a low density like Jupiter, which is made up mostly of hydrogen, or is it something in between? So what we've plotted here for all the planets that we know both those numbers for, how big the planet is versus its density. And you can see a couple of things. First of all, in general, if you get down to very small planets, they have relatively high densities, and as the size increases, the density increases. If you look at large planets, like they're out here, like Neptune's, they have low density, but as they get smaller, the density increases. And there's a lot of scatter. So let me explain what might be going on here. For the small planets, if these are all rocky, then as they get bigger, then their self-gravity will compress them more and they'll get more dense. But if you're out here and you have a gas giant, then as it gets more massive, then it's going to contract a little bit and it's going to get smaller and therefore more dense. And so what we think is these are rocky planets, these are gas giants or planets with very large atmospheres like Neptune, and there's a crossover somewhere around 1.5 times the size of the Earth. So if we're looking for rocky planets, we need to look for planets that are smaller than 1.5 times the size of the Earth. And just some particular planets that are on here. Here's the Earth. I think this is, I'm not sure what, so there's the Earth. There's our older cousin. This planet down here, these planets down here are super puffs because they're kind of big, but they're kind of low in density. Neptune is way out here. And then these guys up here, nobody has a clue. But let me just repeat again that there's, hello? Come on, back. There we go. Let me just repeat again that this scatter here means that, even if you've measured the size like we do in Kepler, you don't really know if it's rocky with a high density or if it's not rocky with a low density, that the size is not, so there's lots of different structures of planets that are the same size. And we have to have another measurement to distinguish between them. Okay, let's move on. We were talking Professor Mustard was talking about looking for biomarker gases in Mars's atmosphere. So that's trivial. I don't know what's up with not being able to measure the methane in Mars's atmosphere. Mars is just so close and so easy. But let's talk about measuring the methane in a planet which is tens of light years away. Okay? In order to look for evidence, so the real thing we want to do is to know, did life arise on planets around other stars? And let's see, how am I doing? Not too good. But I do want to say that, you know, there are habitable environments in the solar system besides the Earth, Mars, Europa, maybe other places. And we found that there are lots of rocky planets in the habitable zones of their stars, and those might also be habitable environments in the galaxy. And hopefully, wherever there's a habitable environment, life might arise. But if you've got 2 or 3 places in the solar system, that's all the places you can look. If you've got hundreds or thousands of exoplanets to look on, that's a lot more places to look. So we really want to be able, if we really want to answer the question, did life arise elsewhere other than on the Earth, we really want to be able to look for signs of life on planets around other stars. Now, I don't know how or when we'll ever be able to image them and look for the city lights or what else on them. But we already know that we can sample their atmospheres in several different ways. And we can look for the signatures of various gases in the atmosphere. And you can look for signatures of ozone, which would be indicative of oxygen. And as we heard about the Earth, oxygen is a process, byproduct of biology. It didn't occur naturally on the Earth. We can also look for water in the atmosphere. We can also look for methane in the atmosphere, which could be biological. You can also look for the red dip, which is caused by chlorophyll, if you have photosynthesizing plants on the planet. So basically, if you could get a spectrum of the reflected light from a planet around another star, you want to look for evidence of gases which are not in thermal equilibrium, not in equilibrium, but are being driven out of equilibrium by a biological process. Okay, so what does it mean to try and do that? Okay, I'm going to skip this one. That's just to show you that never mind. So in order to be able to do that, what do we require? First of all, we want a system that's sensitive enough that we can do this for more than one, right? Just doing it on Proxima Centauri b isn't good enough. We want a system that can do it, say, out to 50 light years. So we'll make sure that we have dozens of rocky planets in the habitable zone to study. We need to be able to separate the star from the planet so we can look at just the light from the planet. And the planet is 1 billion times fainter than the star. So separating these out is very important. At 50 light years, the habitable zone is less than 1/100th of an arc second across, less than 1/10th of an arc second across. And so you need to be able to resolve better than the Hubble Space Telescope, but only a few times better than the Hubble Space Telescope. And also, you need to be able to reject the star's light and collect the planet's light. So that's 1 part in 10 to the billion if you're looking at an Earth-like planet next to a Sun-like star. So what kinds of systems might do this? Well, the first thing is a coronagraph. A coronagraph is a system where you have a special camera, and inside it you have a set of blockers and lenses that will completely reject the light from the star while letting the light from the planet pass. It has to be good to 1 part in 10 billion, or the starlight is going to be more than the planet light, and you won't be able to measure the light from the planet. And so this requires mirrors that are stable to 1/1000th the size of the wavelength of the light you're trying to measure, for instance. But in the laboratory, we're able to do that. Okay? We're able to do that in the laboratory. And we are building the first space system to do this. The next large observatory that NASA will build after the James Webb Space Telescope is the Wide Field Infrared Survey Telescope. It'll have 2 instruments on it. One of it will be a technology demonstration coronagraph that will be capable of seeing exoplanets and rejecting the starlight and allowing us to measure the light from those exoplanets. Now, because WFIRST is the same size as Hubble, its mirror is only 2.4 meters across, we can't resolve Earth-like planets. It's a mirror size limitation. But we will be able to see Jupiters and Neptunes and maybe even mini Neptunes around the nearby stars. And this mission will be launching around 2025. The second way to do it is to have an interferometer. Interferometry is where you have two mirrors that are separated. The light comes in at slightly different angles. By combining them, you can reject the light that's exactly in the direction of the star, accept the light that's in the direction of the planet, which is a slightly different direction. We are testing that out with NASA's Large Binocular Telescope Interferometer, which is right here on an observatory on Mount Graham in Arizona. And then the third methodology is very cool. It's called a star shade. So you have a space telescope, and you have a blocking disk that is 50,000 kilometers. So this is not to scale. Away from the space telescope, okay, and it casts a shadow. And anything which is directly in line will cast, like the star, will cast a shadow on the telescope. But the planet is offset from the star, and its light gets past the edge. And the very funky petal shape is to make sure that your diffraction patterns from the star all null out, and you can see the planet next to it. So we've got star shades about this big in the lab, and we're demonstrating that this is possible. So this is not something we're currently building. It's something we're trying to figure out how to build, because this thing is 34 meters across, not going to fit in a rocket, has to fold up, has to unfold, has to be stiff. You have to be able to get it in the right place to within 1 meter and to within 250 kilometers. So this is a lot of hard problems that have to be solved all at once. And so we don't know, A, is this easier or harder than a coronagraph? And we don't know, B, which one gives the best science. So we're studying both of them, and we're going to make that decision later for a future observatory. NASA has launched the Hubble Space Telescope, Spitzer, Kepler, all of which have studied exoplanets. TESS is our next mission. Stephanie talked about JWST, but JWST will be able to look at exoplanets as they transit in front of their star. You'll see the starlight pass through the exoplanet's atmosphere, and we'll be able to sample that atmosphere by looking at the starlight passing through it. I've told you about WFIRST, which is going to have its coronagraph, and then sometime in the future, we'll either have to have a big telescope with a coronagraph or a big telescope with a star shade to really be able to go after those Earth-like planets around other stars. And that's my story. Thank you very much. We have time for one question. Okay. All right. Yes.
Hi.
Oh, there it is.
In the case for Mars, there's an interesting idea at the end of it, I think. Maybe it was in Entering Space. For an optical interferometer the size of the moon, by scattering telescopes all over the moon, I think on the far side so you don't have Earth shine, what do you think of that idea? I mean, from a feasibility standpoint, I mean, how many would you need? Would it be able to visually resolve Earth-like exoplanets and so on?
So we've done a lot of studies about looking at telescopes on the moon. The moon is a lousy place to put a telescope compared to free space. It's dusty. It's got a really bad thermal environment. And gravity makes your thin mirrors sag, so you'd have to build big, fat, heavy mirrors. Whereas in space, you can have thin mirrors that have exactly the right shape. You have no dust or obscuration that's going to dirty your mirror. And you can get, like JWST, in a place where it's thermally very, very flat. And thermal is important because mirrors and telescopes change as the temperature changes. So, it turns out that planetary surfaces are not the best part for telescopes, whether it's the backside of the moon or the Earth itself. I really like space telescopes.